Good morning, friends. Welcome to the second session on for the talk on gears. So, in the first session, we would have talked about the motivation for using gears in different machines. So, I hope you are clear with that. We took ourselves the objective of studying spark gears in particular. We understand there are different types of gears in practice, but as we iterated that this course is going to be about spark gears specifically. The reason being that spark gears are the simpler ones. So, the other gears such as helical or spiral gears are a little more complicated in terms of its geometry, but none the same, if spark gears are understood well, it should be possible for you to learn out those subjects as well in a more advanced. We spent a lot of time in defining the different parts associated with the gears. So, we dissected out the gears and sort of named the different parts of the gear as per standard terminologies. Now, today we will begin our study on the very important topic of involute gearing. So, that is the agenda for the first part of the talk today. This is where we left. We talked about higher pair mechanisms. Higher pair mechanisms, just to revise that part, are those mechanisms wherein there is a line contact between the two links, and as is shown here, the red and the blue object are forming a higher pair mechanism, and between the red and the blue body, the relative motion that is possible is there are two types of relative motions which are possible. One is that of relative sliding, which is shown on the diagram on your left, and the other is that of pure rolling, that is rotation without slipping. But it does happen through the arguments that were presented in the previous class, that in either of these motions we see that the instantaneous centers lie along the normal to the point of contact. So, here we have shown two bodies which are circular shapes. So, the instantaneous center in case of relative translation alone will be actually the instantaneous center will coincide with the center of curvature of this blue body if the red body is sliding on top of the blue body. So, in that case this is the instantaneous center. In the other case where it is having a pure rolling action, rolling without slipping, in such a case then we will have the instantaneous center again at the point of contact. So, again in either case it is easy to understand that now if you have any combination of motion, it is pretty easy to understand that the instantaneous center between the higher pairs will always lie along this common normal. So, this will form a very important starting point for the argument of fundamental law of gearing, as we will show in the next slide. And we understand that for gear tooth, finally we are interested in this course about gears. So, when it comes to engagement between the two gear tooth, the gear tooths are forming a higher pair mechanism, because firstly we have seen that the gear tooth pair will in 2D view, in the front view of it, it is having point contact, or in 3-dimensional it will have a line contact. As such, it is a higher pair mechanism, and therefore the instantaneous center will lie along the common normal as is shown here. So, here I have sort of blowed up the engagement between two gear tooth. So, what is shown here is just the gear tooth. The geometry of is actually irrelevant. I have taken a very general gear tooth profile and tried to illustrate what would be the instantaneous center between these two gear tooth as it is engaging and disengaging. So, here is a very general profile. Obviously, this is not something which will be seen in reality, but none the same it is much more general in the sense that our actual gear tooth profile is also like a special case of this. I have not assumed this to be involute or cycloidal or anything. I have just taken an arbitrary gear tooth profile, so as to say, and I am trying to illustrate how do we find instantaneous centers between two meshing gear tooths. So, towards this end, my first realization is that between these two objects, which if you may call as like rotating cams, there we have a point of contact alone. This is not a surface of contact, this is just a point of contact in the front view of it, but now if you think in 3 dimension and visualize the thickness of this object, then you will infer that there is a line contact between these two bodies. So thus the two bodies which are labeled as body 2 and body 3, body 1 being the frame with respect to which the two bodies are moving. So it is therefore known that these two bodies, body 2 and body 3, are forming what are known as higher pair mechanisms, as we just illustrated. So because they are forming a higher pair mechanisms, as we illustrated, the instantaneous center has got to lie along a common normal. So this is as indicated in this red dotted line, right. Also what we know is that this body 2 is pivoted at this point. So because the body 2 with respect to the frame, which is body 1, is undergoing only relative rotation, and that relative rotation is about the pivot point. So the pivot point definitely, or the revolute joints, are the instantaneous centers between body 2 and body 1, and similarly body 3 and body 1. So body 2 and body 1 both are fixed to body body 2 and body 3 are both fixed to the frame with the help of revolute joints. So therefore the location of the revolute joint is exactly the instantaneous center of body 2 with respect to body 1, and similarly body 3 with respect to body 1. So accordingly the instantaneous centers are marked in this diagram as I12 and I13. Now as we argued, I23, which is the instantaneous center between body 2 and body 3, will lie along the common normal, but we do not know where exactly on the common normal this body lies, because we cannot say whether these two bodies are in pure rolling or whether it is rolling with sliding. So if it is rolling with sliding, obviously then the instantaneous center does not come at the point of contact, but none the same it has to be on the common normal. So at this point the only inference that we can make regarding the relative motion between body 2 and body 3 is that the instantaneous center is somewhere on the common normal. We do not know exactly where on the common normal the instantaneous center lies. But then we have the famous Aronhold-Kennedy theorem, which we learnt in mechanisms. So the Aronhold-Kennedy theorem says that if you have three bodies, then the relative instantaneous centers between these three bodies will be collinear. So here we have an application of Aronhold-Kennedy theorem which demands that there has to be three bodies. Here too we have three body. The first body is obviously the frame, which is the stationary body, so as to say, with respect to which all other motions are taking place. And we have two moving bodies with respect to the frame, which is body 2 and body 3. So definitely we have three bodies. We also know exactly two of those three relative instantaneous centers. We know exactly the location of I12, we know exactly the location of I13. We do not quite know the where the instantaneous center between 2, 3 lies, but at this point we only know that it has to be lying on the straight line joining I12 and I13. So Aronhold-Kennedy theorem tells that the instantaneous center between 2 and 3 has to lie on the line which is joining the two pivots or the two revolute joints, whereas our previous argument said that the instantaneous center has to be on the common normal. So therefore the only way out in which both these arguments will hold is that the instantaneous center between body 2 and body 3 will actually lie in the intersection of these two red dotted lines, that is the common normal and the line joining the two revolute joints. So if on the line joining the two revolute joints is shown by this horizontal red dotted line, and the common normal is shown by this line which is little bit slanted. So the intersection, if you can see, is what is shown as the point P or point I23. So the point of intersection between the line joining the gear centers, which is the revolute joint, and the common normal is the instantaneous centers between body 2 and body 3, and that is denoted as I23 or P. So we will see the importance of P. Now we know by property of the instantaneous centers, the relative motion, whether you observe the motion of body 2 at whether you observe the motion of the instantaneous center, which as we have now seen is this point. So the motion of this point P or I23, whatever you may call, this point P, the motion of this point, if I consider this point to be attached to body 2, will be same as the motion of this point P if I consider this body to be attached to body 3, if I consider this point to be attached with body 3, right. So let me repeat my arguments just once again for the sake of clarity. By definition, instantaneous center between the body 2 and body 3 is defined to be a characteristic point such that if that instantaneous center point is assumed to be attached to the body 2, then whatever velocity we get, that velocity should be identical if this instantaneous center point is construed to be attached to body 3, right. So let us just quickly elaborate this argument once again. So here we have two arbitrary bodies, this is body 2 and this is body 3, and they are rotating about revolute joints with respect to the frame. So it was found that the instantaneous centers between these 2 points lies somewhere here. So this is P is I 2 3, okay. So this is body 2 and this is body 3, and body 1 by convention is just the frame. So if P is assumed to be attached to body 2, okay, I am now assuming this point P is attached to body 2. It does not matter if the point P actually lies outside the physical extent of the body, that is irrelevant. I can still consider a fictitious extension of body 2 and construe this point P to be attached to body 2. If I make such an if I construct such a hypothetical experiment, then what would be my velocity at point P? If this body is moving at a rotational speed of omega 2, then Vp will be omega 2 into I12 P. So this is I12, which is the location of the revolute joint of body 2. So the distance between the revolute joint to the point P multiplied by the angular velocity is definitely the velocity of the point. Now similarly, I can assume this body to be, this point rather, point P to be attached to body 3, okay. If I make such an assumption using just the similar arguments, I find Vp has got to be omega 3 into I13P, where omega 3 is going to be the rotational speed of body 3 and I13 is the location of the revolute joint which connects body 3 to the frame. So again the velocity of point P, which now I am assuming to be attached to body 3, is just the rotational speed multiplied by the radius vector joining the revolute joint which is located at I13. But now by definition of P being the instantaneous center between bodies 2 and 3, these two velocities which we have calculated, so omega 2 I12P has to be equal to omega 3 I13P, okay. So this is a very important qualification which sort of characterizes the instantaneous center between two bodies in relative motion. Whether you construe the point to be attached to one body or the other, either way you end up getting the same velocities. This analysis will not hold for any other point in this mechanism. It is only this point P which will have this special property that P, whether you consider this point P to be attached to body 2 or to body 3, either way the velocity is same. If you consider any other point Q which lies over here, then velocity of Q, if it is assumed to be a part of body 2, is not the same as velocity of Q if it is assumed to be a part of body 3. It is only this point P for which this relation holds, not for any other point. So with that explanation, I hope you get the point that by property of ICs we have this condition to be true. Now we come back to gears. So if you recall the reason why we are using gears, what we want is the velocity which is generated at the engine output shaft or the motor output shaft, that velocity we want either a reduction or a gain, and accordingly a torque gain or a reduction. But we definitely want a constant velocity ratio. That is, whatever is the input speed that is coming to your transmission or to the input gear, that should get amplified or reduced, but then it should not fluctuate. Let me again illustrate that what I mean through some writing. So let us consider two gears. So this is one gear, the input gear, and this is the output gear. So we understand the input gear will have angular velocity omega 2 and the output gear will have an angular velocity of omega 3. Obviously omega 2 is not equal to omega 3 in general. We do not demand that omega 2 and omega 3 has to be equal, but all we demand is that omega 3 by omega 2 is constant for all time, right? Because let us say that the engine generates a constant speed, but if because of your transmission omega 3 starts fluctuating, then that could be catastrophic. So in other words, let us say that the engine output or the motor output shaft, if you take a tachometer and measure the rotational speed, it is dead constant. What you want is, this is omega 2, what you want is omega 3, it need not be at the same value as omega 2, but it could be at different value, but what is most important is that the value itself should not change with time, it should be constant. What is not allowed is that you should not have a fluctuating engine speed, output speed as this, because if you have a fluctuating output speed, let us say in your machine cutting operation in a lathe, then a fluctuating output speed will be detrimental to the surface finish. Similarly, in the automotive example, you do not want the output of the transmission, which basically becomes the input of your gear of your wheels. If the input of the wheels starts fluctuating in terms of speed, then the drive quality of your vehicle will be severely compromised. So definitely you wish to get a constant angular speed at all times. The effect of transmission should only be to increase or decrease the input speed by a fixed amount. It should not be changing with time, and this we will realize is a very severe requirement actually. It might seem to be a trivial requirement, but this is actually a very important and a severe requirement which essentially enforces the condition that not any arbitrary tooth profile such as a straight tooth profile is allowed. So we will see that in a moment's time. So as I said, what we require from our gearing is the following: we want a constant velocity ratio omega 2 by omega 3 in our gearing system. But now as I said that these in this figure we could assume these two to be exactly like two mating gear tooths. It is just that I have not drawn it like a gear because it will be cumbersome to do so. I have just tried to draw two gear tooths, and at the end of my analysis what I see is omega 2 by omega 3. This ratio will be kept constant only if the ratio of the distance from the instantaneous center to the revolute joints, that is omega 2 by omega 3, is constant. If I13P divided by I12P, this second ratio is constant. So, the requirement that omega 2 by omega 3 is constant effectively means that, so if omega 2 by omega 3 is constant, that effectively means I13P divided by I12P has to be constant for all times. It cannot change. But then what is this ratio? This ratio is exactly the distance from the two shaft centers to the pitch point. So, the ratio of the distance should not change. So, pitch point should be therefore, or this point P, I should not have used the word pitch point. At present this point P is just the instantaneous center. So, in other words, the requirement now boils down to the fact that that this point P, the instantaneous center between the two meshing gear tooth, should be such that the ratio of these two distances have to be fixed for all time. But this ratio can be fixed, this ratio of these two distances will be fixed if and only if the point itself is fixed. If the point moves around on this line or on any other line, then it is not possible that it will that this distance is going to be fixed. So, what we want therefore is that the point P has to be fixed during the course of engagement of the two meshing gear tooths. So, as I said, for transmission of constant velocity ratio at all times, the common normal between the mating gear tooth must intersect the line joining the gear centers at a fixed point. Because if it does not, let us just try to illustrate what happens if this condition is not true. So, let us say between two meshing gear tooth, so let us say this is one gear tooth at a certain instant. I am just interested in showing the engagement between one gear tooth. Okay. So, here we have this as the common normal, and I should have drawn the shaft somewhere else. So, the shaft center is, let us say, somewhere here. So, the pitch point, or sorry, the point P, or the relative instantaneous center between the two bodies, this is the body 2 and this is the body 3. The relative instantaneous center, or the point P, which incidentally will turn out as the pitch point for our gears, this point P is at this instant located here. But let us see what happens when the engagement is at a different point. So, at a later instant, let us say the gear has rolled, and this is where the engagement is taking place. The shaft centers again lies somewhere here. Okay. So, again the relative instantaneous centers can be located to be the intersection of the line joining the shaft centers and the common normal between the two surfaces in contact. So, again now this is the point P. So, at this instant, so this is instant T1 and this is instant T2. Now, at this instant omega 2 by omega 3, this is I13P divided by I12P. At the other instance, let me call this point as P prime, because I am assuming that this point P is not coincident with the point P prime. So, at this instant omega 2 by omega 3 is again I13 P prime by I12 P prime, right. note in either of this case I13, I12 does not change, but P changes to P prime. Okay. So, if P changes, but these two points which is I12 and I13, these 2 points have not changed, these locations have not changed. So, that means the ratio, so this implies I13 P, the distance between the point I13 and P, and the distance between the point I12 P, the ratio of this cannot be equal to I13 P prime divided by I12 P prime. These ratios cannot be the same, which means omega 2, I will call this omega 2 prime and omega 3 prime. So, this means omega 2 by omega 3 at the instant T1 is not the same as omega 2 prime by omega 3 prime. In other words, even if the input speed is same, the output speed is going to differ, it is going to fluctuate. This is something that we do not want. This is a very strong requirement and we must enforce it. So, we will see therefore that the only way in which we can enforce it is that this point P should not move. If the point moves to a different point P prime, this condition will not be enforced. So, the only way in which omega 2 and omega 3 can be kept fixed is that this point which is formed at the intersection of the common normal between the two tooth profiles and the line joining the shaft center has to be fixed. So, we must have a fixed point of intersection between the common normal and the line joining the gear center, and this is also called the pitch point. Remember, in the last class we had defined pitch point as the point which is tangent to the two pitch circles. So, if we replace this motion transfer with the friction disk problem, then you will realize that for the friction disk problem, again omega 2 by omega 3 is given as R3 by R2, which is in other words to say that the angular speed is inversely proportional to the radius, and the radius is exactly the distance between the shaft center and the point of tangency, which is P. So, this omega 2 by omega 3 is also equal to, so if we replace this disk now, if we replace the engagement now by two friction disks, okay. If we replace this by friction disk at this instant, okay, at this instant whatever is the motion transfer happening between our gears, this is the motion transfer happening between the gears. So, whatever is that motion transfer, identical motion transfer is going to happen between the friction disks which are of the size of the pitch circle, because that is the definition of pitch circle, that it will transmit exactly the same motion as is transmitted by the gear. So, now at this point P, omega 2 by omega 3, if I again call this as I12 and I13, sorry, then this omega 2 by omega 3 is exactly I12P or I13P, I should have written this thing neatly. I13 is times P, or the distance between the points P, which is the point of tangency between the two circles, and the revolute joint between the disc 3 and the frame, this is disc 2. So, omega 2 by omega 3 is I13 time the distance between I13 and P, which is this distance. So, this is I13 P and this distance is I12 P. So, this is the condition that we would have got on the equivalent friction disks which are transmitting the angular motion at this instant. So, now this ratio we can identify to be the ratio of the two radius of the two friction disks, and therefore, this point P comes out identical to be the pitch point of the friction disk. So, that is the equivalent of equivalent motion. So here just to repeat the arguments, these were the 2 points. This is the common normal, which means this is the point P, which the manner in which we have defined this point P for gears, it is just the relative instantaneous center between the 2 rotating gears. But then if the angular velocity ratio between the 2 rotating gears have to remain constant, the distance between the relative instantaneous center and the shaft centers of the 2 gears have to remain fixed. Now if we strike the equivalence between the motion of the 2 gears and the friction disk, what we are going to see is that this equivalence is going to happen if and only if this point P remains fixed, and the point P for the case of the equivalent friction disk happen to be that of the point of tangencies between the 2 pitch circles, and therefore the point P is basically identified as the pitch point or the point of tangency between the 2 pitch circles. Okay. So this is the important requirement, and which is what gives us the fundamental law of gearing. So therefore the fundamental law of gearing states the following, that for transmission of constant velocity ratio at all times, which is a very important requirement driven by practical consideration, the pitch point must remain fixed. So any gear tooth that is under operating conditions should maintain a transmission of a constant velocity ratio, and therefore for such gear tooth the pitch point must remain fixed. Now it is very clear that why arbitrary tooth profile such as a straight gear tooth profile, straight tooth profile for the gears is not allowed, because this condition will not be satisfied by an arbitrary tooth profile such as a straight tooth profile. In fact, a straight tooth profile will have lots more problems, but at least one very important problem is that it will not be able to transmit a constant velocity ratio, because when it will be engaging, then the pitch point between the straight tooth profile or the relative instantaneous centers between 2 such gears which are cut out in the manner of straight tooths, they will not be able to maintain a constant pitch point during the entire course of engagement, and that is why straight tooth profiles will not be allowed. So mating tooth profiles which satisfy the condition that the pitch point remains fixed or the relative instantaneous center between the 2 moving gears is fixed, that sort of tooth profiles will be called as conjugate profiles, and we will take only conjugate profiles as practical profiles, because practically we want the constant velocity ratio condition to be maintained, that cannot be compromised with. We should not let the gear change the velocity ratio at different times or the torque ratio at different times, because that could be detrimental to the performance of the gearing. So therefore to maintain a constant velocity ratio, we need the fundamental law of gearing to be satisfied, which says that the pitch point should always remain fixed during the entire course of engagement, and gear tooth profiles which in fact satisfy such conditions will be known as conjugate profiles. And now we will come to the very important inference which I will prove in due course, that involute tooth profiles are conjugate. That is why we do not use straight tooth profiles, we use a very specific tooth profile. I will come to the definition of involute tooth profiles and so on. But involute tooth profiles, one major advantage is that they are conjugate, which means if you use gears for which the gear tooth is having a specific geometrical form which is called involute, then you are sure that the velocity ratio that will get transmitted will be constant. But again I wish to say involute tooth profiles are not the only conjugate tooth profiles, there are other conjugate tooth profiles also, but as I will show you, involute tooth profiles have other advantages apart from being conjugate. So therefore involute tooth profiles wins hands down, and predominantly in most gear applications you will be able to see involute tooth profiles in actions, and therefore we will limit ourselves to involute tooth profiles and will describe how involute, what is exactly an involute, the geometry of an involute, and then we will try to prove that yes, involute tooth profiles in fact satisfy the fundamental law of gearing, and therefore they have an advantage in terms of other arbitrary tooth profiles. Okay, before I start my discussion on involute tooth profiles, I would like to show you an animation which is just downloaded from Wikipedia. This exactly elaborates the point that I have just mentioned. So in your screens now you could see two gear pairs which are engaging. Now here this blue dotted line, if you can observe, is the common normal, but please note that the common normal at the point of contact here is not changing. Always this blue dotted line, if you carefully observe, this blue dotted line remains common normal during the entire course of engagement. So this animation exactly shows the course of engagement and disengagement between one tooth pair, and if you carefully observe, then you can find out that the blue dotted line always turns out to be the common normal. So then the pitch point, which can now readily be identified as the point of tangency between these two red dotted lines. So if you can see the red dotted circles, these are the pitch circles. So this is the pitch point, and if you observe that the blue line always passes through this point. This will also pass through the line joining the shaft centers, which incidentally is not shown in this animation, but I have placed my mouse cursor exactly at the pitch point. So if you can see that the common normal during the entire course of engagement always remains same and always passes through this pitch point. So in other words, pitch point, which is exactly the point where I have held my cursor, that pitch point is going to be fixed during the course of engagement, and pitch point being fixed during the course of engagement essentially tells me through the fundamental law of gearing that this assures that the velocity ratio is constant during the process of engagement, and therefore these tooth profiles are conjugate. Incidentally, these tooth profiles are involute. I will tell you more about involute in just a short time, but I wish to make myself a little more clear through by showing you these visualizations. Again, I wish to reiterate, this visualization is not done by, this animation is not done by me or my students. It has been posted free in the Wikipedia site. So I am using it with due credits to the Wikipedia author who has made it. So please look at these animations to get yourself a visualization as to what exactly is happening. I will show more animations also. One more animation I wish to show probably later in this course, but at this stage I will possibly before getting into involute, I will pause for a while and take a few questions from you if you have any, and then we will proceed with the study of involute geometry, what is called involutometry. So please feel free to ask questions at this stage if you have any, else we can proceed. Okay, we have a question from BEC. Why gears slide only along common tangent and why not along common normal? I think you need to understand the gear geometry. I don't think you got the first part right, that it is sliding along the common tangent. So please understand, if these are the two gear tooths which are in engagement, right. So at an arbitrary point during the time of engagement, at the point of contact, the velocity of the point of contact as seen from this body 2. So as usual, I will call the two gears as body 2 and body 3. So this is the point of contact, which I will call it as C to make myself quite clear that this is not the pitch point. Now at this arbitrary point of contact, which does not coincide with the pitch point, this is the radius from the shaft center, which means that the velocity is perpendicular and the value of Vc, if it is assumed to be a point in body 2, is going to be omega 2 times, so this is I12, so I12 times C. I12 distance between I12 and C. So this distance is I12 and C, right? Now again from geometry we realize that if VC is now taken as a point in body 3 and this body is moving at a speed of omega 3, whereas this body is moving at a speed of omega 2, right. Now again the velocity for the point of contact now will be perpendicular, which is here, right. So this vector denotes VC if it is taken as a point in body 2, and this vector denotes VC taken as a point in body 3, right. Obviously the two velocities at the point of contact doesn't coincide. So therefore their tangential components doesn't coincide, but the normal components will definitely coincide because they have to maintain the engagement during the entire process of meshing. So therefore there is sliding that is allowed at the point of contact, except when the point of contact itself becomes the pitch point. So the gears definitely have the type of action which is taking place between the gears definitely includes sliding between the two gear tooth, and the sliding demands that along the tangent of the two gear tooth the direction of velocity is not the same, right. But to maintain the contact for all times during the process of engagement, then the velocity in the normal direction has to be the same. Otherwise if the velocity in the normal direction is different, then the contact will be lost. So that is the reason why you have that criteria that velocities in the along the common tangent will be different, but velocities along the common normal will be same. So I take that question as answered. Please write your questions in the question box rather than the chat box. That will help us do the bookkeeping correctly. Number of KNMU is asking the number of tooths in gear and its effects. We have not talked about the number of tooths in gear, other than the fact the number of gear tooths is related to the number of to the radius through the module. But in the last class, if you remember, that we have said that the exact reason why we are using gears is to increase the torque or the speed. So as we will see that the gear ratio is basically a ratio of the radius, but then if you have to manufacture gears or if you have to design gears, then everything is standardized with respect to the module, because module fixes the cutter for the gear, and then if the module is fixed, if the radius is fixed, that becomes a relation for your number of tooth, and number of tooth will have that you have decided upon, that has important repercussions in the sense that interference may or may not happen depending upon the number of tooth that you have for your gear. So the number of tooth criteria for a gear is actually relating to the interference, which we will come to at a later stage. Okay. KECP is asking if pitch point is not fixed, what about velocity ratio? I exactly said this, the same thing. If pitch point is not fixed, velocity ratio is not going to be fixed. If pitch point moves during the process of engagement, then the velocity ratio will also move. This is exactly what is called as fundamental law of gearing. Because of fundamental law of gearing, it is demanded that if velocity ratio has to be fixed, then the pitch point has to be fixed. If pitch point does not remain fixed, velocity ratio will not be fixed. So that answers the question from KECP. KECP is asking the next question on gear train. We'll come to gear train probably in the next session, but just to give you a quick answer, gear train is a collection of gears. Sometimes you will not be able to achieve the required gear ratio simply by using one gear pair, because that would mean that one of your gear is very large and very bulky. If you have a large bulky gear, that means it's a large mass. A lot of energy is wasted simply to rotate the gears and to make it move from its state of rest to its state of motion. So therefore that accounts for some energy wasted. So you should not go for large bulky gears, rather you should go for small gears but maybe a number of them such that you can attain any gear ratio that you want. So that is coming in what is called as gear train, which is a collection of gears. So we'll come to gear trains probably in the next class. Okay, that is answered. I don't see any hand raise also. Okay, so looks like how to decide about gear size. Yeah, so BEC is asking how to decide about gear size. So gear size is decided based upon gear ratio and the condition of interference. So if you choose too small gear, then you may have too less number of teeth in the gear for the same module, that is, and that may cause problems in interference. So there is a condition wherein we have to check that the gears have minimum number of teeth so as to avoid interference, and the gear ratio, once that is decided, module is decided, then we should be able to choose the gear size. So I hope I will make myself clear on that as we go along. Since there are no other questions, let's get back to the material in the presentation. Okay, so here is what is an involute. So the involute is the locus of any point on the string as it is unwound from a circle. So involute of a circle, to be more specific, is constructed in the following manner. We first wound up a string on this circle, and then as we unwound the string, then any point on the string is going to trace out what is known as the involute of a circle. So the involute, when we say involute, we generally mean involute of a circle, but you can understand that involute of any closed figures can be similarly constructed. You could have wound this string even on a hexagon, and then as you are unwounding this string from a hexagon, any point, locus of any point as it is getting, as the string is getting unwound, would generate involute of a hexagon in that case, right. So this is the general idea of involute, but at least in this talk, when I am talking involutes, I generally mean involute of a circle, right, because that's in the context of gears, that is pretty obvious that involutes are generally taken on a circle. So the definition, the technical definition of an involute goes this way, that it is the locus of any point on the string as it is unwound from the circle, and this generates an involute. So as we will show that it is this tooth profile, involute gear tooth profile, which satisfies fundamental law of gearing. But as I said, this is not the only gear tooth profile which satisfies fundamental law of gearing. Satisfaction of fundamental law of gearing for involute gear tooth profiles is one criteria, or is rather one advantage because of which we use involute gear tooth profiles, but there are many others as I will elaborate. So what I mean to say is that till now what we were drawing these gear tooth profiles as arbitrary. Now if we in fact make sure that our gear tooth profiles are involutes, both of these are involutes, which means that they have been generated from some circle, okay, by unwinding strings from some circles, then we are sure then that this mesh will satisfy the fundamental law of gearing. So this is an involute, this is also an involute. So when the gearing action takes place between two tooths which are made out of an involute form, then fundamental law of gearing is satisfied. So if gear tooth profiles are involute, of a circle, that goes without saying, then the fundamental law of gearing is satisfied. Which means involute profiles are conjugate. As we just said that conjugate profiles are those profiles which satisfy our criteria for fundamental law of gearing. So, the statement now is that involute gear profiles will be conjugate and we will tell you why. So, hang on for some time for that. And the circle over which it is being unwound. So, as I said, the definition itself of an involute starts by saying that it is the locus of a point on a taut string as it is unwound from a circle. The circle from which this string is getting unwounded is called a base circle. So, this is a very important terminology, that a base circle is the circle over which the string is getting unwounded so as to generate the involute tooth profile that we are looking at. Okay. So, here is a very important visualization, and again I will try to complement my lecture with a nice animation, but let us first do the lecture once and then we will again spend some time looking at the animation. So, here is what is known as a cross belt pulley analogy. So, as we said, as we rather stated without proof, that is that involute tooth profiles are conjugate. In other words, if we make gear tooth profiles in the form of involute, then we are hoping that the constant velocity ratio criteria will be maintained, which means that fundamental law of gearing will be satisfied. So, now we are going to prove this with a very intuitive idea, which is called the cross belt pulley analogy. So, here is how it goes. So, we consider two pulleys, one is the driver pulley and the other is the driven pulley. So, here the driven pulley is, I think the marking is wrong. So, we can take it take this as the black pulley as the driver pulley, and it is getting so the string is getting wound up in the driver pulley, and the way this is the motion that is shown here which is anti-clockwise for the blue pulley. So, that the belt is getting unwound. So, this is a typographical error. So, the blue pulley is the driven pulley and the black pulley is the driver pulley. Okay, so sorry about that little mistake. So, here what we get to see is the following. So, now as the pulley is performing its job, which is to transmit motion from the driver to the driven. So, remember, the two pulleys are getting connected through a cross belt drive. So, cross belt drive is like a tangent which is internal to the two pulleys. Now, because of the action of the pulley, the cross belt drive is going to get wound into the into the driver pulley, and it will get unwound from the driven pulley, right? Because the driver pulley it's on this black pulley, it's going to get wounded up this belt, and it will get unwounded from the blue pulley. Now, if you look at any point of this belt, any point on this belt as you are looking at it will definitely move in a straight line. That is unquestionable, because each point is just moving from here to here to here and finally to the point of tangency of the driver pulley, right. So, that is not difficult to visualize. But now, if we think that we are sitting not on the inertial frame, but we are sitting on this blue pulley, then what happens? So, with respect to the blue pulley, we will see that the string is getting unwound as the blue pulley is fixed, right. So, definitely we understand the string or the belt, whatever you call it, that belt is getting unwound from the blue pulley as the motion is taking place. So, that by definition should generate an involute. So, as this belt is getting unwound from the blue pulley or the driven pulley, then it is going to generate a curve of the form that is shown. That is definitely an involute. At a later instant, this point would have travelled here, and you will now be able to see a greater part of the involute, right. So, in nutshell, or to reiterate once again, what we have is two pulleys between which there is a cross belt that is connected. As one of these driver pulleys is moving clockwise, the driven pulley is moving anti-clockwise, and when this motion is taking place, any point on the pulley as seen by the observer on the inertial frame, any point will definitely execute a motion which is along this tangent, which is basically a straight line. But then for an observer who is seated on this pulley itself, to that observer it will simply appear that the string is being unwound by some mechanism, right. That observer who is seated on the pulley itself will not realize that the pulley is rotating. For him the pulley is fixed, it is just that the string is getting unwound. So that by definition is an involute tooth profile. So therefore, if this point is fixed, or rather if I put a something like a pencil on this point on the cross belt, and we put a sheet of paper which is fixed to the driver pulley, to the driven pulley, and therefore it rotates along with the driven pulley. On that sheet of paper we will see that this point will trace out this curve which is shown in blue in both the figures, and this curve is known as the involute curve, again by definition. For the red part of the curve it is just the opposite. So instead of unwinding the string, here the string is getting wounded up. So on the driver pulley the string is getting wound up, which is what you will see. So as the string is getting wound up, it is just the reverse motion, if you may like, it is going to generate this red curve. So if I now put this pencil which is fixed on to the onto a fixed point on the belt, and now I put this piece of paper on the driver pulley, that is this black pulley, and see what is the curve that is getting traced out. So this is the locus of a point on a string as it is getting wound up on to this circle, right. So that also by definition is an involute. So winding and unwinding are just two reversible processes. On the blue pulley it is getting unwound, and on the black pulley it is getting wound up. So therefore on the black pulley also it will generate an involute. So this is how we can generate two involutes on these two pulleys or these two circles. So this is exactly what I said, that consider a cross belt drive between the two pulleys. In the reference frame of the pulley, a point on the belt traces an involute. Whether you consider the reference frame to be that fixed with the blue pulley or that fixed with the black one, in either case it is going to generate an involute. So the important inference therefore is that the point of contact between these two is between these two involute profiles is exactly lying on this cross belt, which is again the internal tangent to the two circles. So the point of contact between the red and the blue involute is, as you can see from these graphs, is going to lie exactly on the point on the belt, and the point on the belt is definitely on the internal tangent between the two circles. The point of contact, we can conclude, between these two involutes will lie on the belt. The belt is the common normal between the two between the two circles. It is also the common normal between the two involutes, because just look at the condition of the contact that is happening here. The common point of contact here and the common at the common point of contact, you will get the common normal to be exactly this belt. So the belt is the common normal between the pulley, because again I could prove this from definition. Just think about an infinitesimal time duration that is taking place as you are unwinding. So as you are unwinding, the string will be perpendicular to this small little distance T1. So T1 will be perpendicular to the string itself. So using that logic, it should be at least intuitively clear to you that the point of contact between the two involutes lies on the common normal between the two circles. The common normal between the two circles also form the common normal between the two involutes itself. So belt is the common normal between the two involutes. And now what we will do is that we will cut off the belt, and we will say instead of the motion transfer being occurring through the belt, let there be a force which, let's say, the let there be a force which one pulley gives onto the other. So let's say the blue pulley is giving the force onto the black pulley. When that happens, then again whatever is the action of the belt, that is getting replaced by a force transfer between the two involute tooth profiles. So the two involute tooth profiles are now engaging, and when they are engaging, there is a force transfer that can happen, and because of the force transfer there will be a motion transfer. That is, there is no, as the question was asked, on the normal side in the direction of the common normal at the point of contact, there is absolutely no difference in motion. If at all there is a difference in motion, it is there on the tangential side, but that is not going to affect the contact condition. So therefore, identical motion transfer is obtained if the belt is replaced by the involute tooth profile on the pulleys. So we could get this motion transfer done either by the belt or by the pulley itself if the pulley is extended with a tooth profile of these forms, and between the tooth profiles we now let a force transfer in the normal direction, which is the direction of the belt or the common normal. So now what this proves is that the motion transfer that is happening because of the belt is identical to the motion transfer that is happening because of the two gear tooths in action. But then the motion transfer which is happening because of the belt has a constant velocity ratio. Therefore, the motion transfer which is happening between the engagement, because of the engagement of the two gear tooth, since it is identical to the motion transfer of the driver cross belt pulley mechanism, therefore that motion transfer between the gear tooth is also having a constant velocity ratio. I understand the visualization is slightly tricky for the beginners, but hopefully you will be able to understand that when you will be able to see the animations which I will show in a moment's time. So therefore, what we now see is the following, that the as the engagement takes place, which is shown, the two time instances are shown here, as the engagement is taking place, then one of these one of these pulleys is generating one involute, the other pulley is generating the other involute, but then the common normal at this point of contact, the point of contact always is a point in the cross belt, and the common normal also is the cross belt itself. So the common normal between the involute therefore remains constant during the entire course of engagement. There is no chance that the common normal will change, because what is the common normal? The common normal is exactly the cross belt between the two pulleys. The cross belt has not changed because the pulleys have not changed. So therefore, the common normal of the two involutes have not changed. So if you recall, this is exactly what was shown in the Wikipedia animation. The common normal between the two engaging gear tooths have not changed during the course of engagement. So this is why we now see it in a geometric fashion, that the common normal between the involutes will remain fixed during the engagement, and if the common normal remains fixed, the intersection of the common normal with the line joining the gear centers will also remain fixed, but that by definition is the pitch point. So if you have the common normal fixed, the point of intersection between the common normal and line joining the gear centers, which is the pitch point, which is the instantaneous center between the two gears, all of them are fixed, and that is what is ensuring satisfaction of the fundamental law of gearing. So the fundamental law of gearing is therefore satisfied between two tooth profiles which are having involute profile, and therefore involute tooth profiles are conjugate. So pitch point remains fixed during engagement because the common normal is fixed, the line joining the gear centers is fixed during engagement. That obviously does not change because gear centers are fixed. The only thing which can change possibly during the engagement is the common normal, but we have seen that by construction involutes are such that the common normal is always the internal tangent between the two pulleys which generate these two involute profiles, and therefore at least for involute tooth profiles we are sure that the common normal is fixed, which makes us believe that the point of intersection does not change during engagement, but by definition that point of intersection is the pitch point, and therefore the pair of involute tooth will satisfy fundamental law of gearing. So this is sort of a proof which I would say is not very rigorous or mathematical, but it is very intuitive and something which requires a lot of visualization, and as I said, I feel for beginners that may be a little difficult. So what I will do now is that I will show you an animation. Again, this animation I must acknowledge is taken from YouTube. This, as I said in the last session, these sort of animations are abundantly available in YouTube, and one of the channels in YouTube which I have also given in reference, which is Kinematics with MicroStation with Ujjwal Rane. So under that channel you have the animation which I am going to show you. There are plenty other animations both in the topic of gear manufacturing and other different mechanisms. So please take a look at it. I hope this animation will sort of help you visualize what I just talked about, and you should be helped with that animation to visualize this proof. After the animation we can again have a open session where you can post your questions to me, and hopefully your doubts will be clarified. So I will now switch over to the animation. It's about a 5 minutes animation. So we'll patiently hear out the animation and then we will take it up from there.
Here we are going to devise a drive to transfer motion under two conditions. Number one, the velocity ratio should remain steady all the time, and number two, there should not be any slip under any load condition. That is, the drive should be positive. Let us start with the first condition, the constant velocity ratio. It is typically made by belt drives like the one shown here. It consists of two pulleys connected with, say, a cross belt. Now this drive gives us a constant velocity ratio, but at higher loads there could be slip. That is, the driver pulley may roll, but the driven pulley may not roll to the expected extent. And this happens because we are using a force which is not very reliable, the force of friction, which cannot increase beyond a certain limit. So instead of using this force where the motion is tangential, let us use a force where the contact is normal. So a direct push is applied. That is the force of contact or the normal reaction. So we are going to replace the tension in the belt by normal reaction. For that we will need a contact between the two pulleys. Since they are far apart, we will have to extend them, and the extension should be such that the contact should be retained even after the pulleys roll. There is a simple trick to achieve this, and that is, we will take a point P on the belt and put a pencil there and draw a shape or a profile or an extension on both the pulleys simultaneously. Since both these extensions or profiles are drawn by a common pencil, they will definitely make a contact at that point, and so the contact will be maintained. To understand what kind of profile this generates, let us concentrate on any one of these pulleys and use this setup. Over here, this is the pulley. To it a cardboard is attached on which we can draw. Instead of belt, we have this inextensible string, and on it there is a pencil. Let us set this in motion, and you can see as the string unwinds and the pulley rotates, relative to that pulley on the cardboard, a curve is getting traced. Now by definition, a point on an inextensible string getting unbound from a circle traces an involute. So what we are getting here is an involute. Now as the string is getting unwound from one pulley, it is getting wound on the other, And it doesn't matter whether we are winding or unwinding. Relative to the pulley, a point on that string will always trace an involute. So we are not only tracing an involute on one pulley, but relative to the other as well. And these two involutes will always make a contact. So this is how it looks. So there is a green involute on green pulley and the red one is getting traced on the red one, and they are always making a contact, and a direct push is applied, thereby the motion is transferred. So there is no chance of slip. So we are not only getting a constant velocity ratio, but we are also getting a positive drive. The best of both worlds, and now we can call this a gear. And because we are using involute profile, this gearing is called involute gearing. We must bear in mind that these two profiles work together as a team to give us a positive drive with constant velocity ratio. They will not work individually. So therefore they are kind of wedded together, an involute working with another involute, and are called as conjugate profiles. Lastly, an observation we can make, that as the two involutes are generated, their lengths are not equal.
Okay, I think we'll keep it that much. I think the next part is not necessary for our talk. I see some questions, so I'll take them right away. So DGI is asking which profile of tooth should be preferred. The answer is involute. Already we have seen one advantage of the involute, that being it is conjugate. So as Mr. Ujjwal Rane also said in the animation, an involute teeth profile on one gear meshes exactly with the involute tooth profile with the other gear. So and also satisfies the fundamental law of gearing. So this is a very important advantage. So this is not true for an arbitrary gear tooth profile. If you take, for example, a straight tooth profile on one gear, then a straight tooth profile on one gear will not be able to mesh correctly with the straight tooth profile on another gear. So in order to standardize gears, because gears are used in large numbers, this involute is probably the best candidate, because one, it satisfies fundamental law of gearing. The involute on one gear is conjugate to the involute on the other gear, and there are few more advantages also, manufacturing wise also it's actually pretty easy. So therefore involute is the preferred tooth profile. There are other tooth profiles like cycloidal. Involute has the problem of interference, so there are to get away with that there are some other kinds of gear tooth profiles, but those are highly specialized. So to answer your question in one sentence, it is involute based on applications. Predominantly it is involute, unless you have a very specialized applications where you need to choose some other tooth profile, like cycloidal tooth profile also is used, but probably not that universally. Okay, so that answers your question. KECP is asking, is it possible to change avoid and interference without changing addendum? Why? We have not talked about interference. We will talk about interference, and we will see that the criteria of interference boils down to a condition of ensuring a minimum number of gears, minimum number of tooth in the gear. If you have a minimum number of tooth on the gear, interference will be avoided. We will see that condition in due course. KECP is asking which mechanical property helps to gear without failure while engaging or meshing. I think you are talking about the material properties of gears. So obviously gears are subjected to a lot of wear and tear. So you will need some sort of surface treatment to be given on gears such that the wear and tear should be avoided. But other than that, from a mechanistic perspective, I don't see what's your question. But regarding material handling, so I mean which materials are useful, you need to look at the material aspects of it. Obviously one thing is known for sure is that gears will be subjected to a lot of rubbing action because of the meshing itself, and in case it is getting worn out, then obviously the involute tooth profile gets worn out, so that's not advisable. So usually this will I mean the idea is to make some surface treatments such that the wear resistance of the gear is enhanced. But this course is not about those surface treatments or about those manufacturing issues. This course is about mechanisms of gears, how the action of involutes enables a constant velocity ratio to be transmitted. So I will take that as answered with that comment. I don't see any hand raise, but maybe I can pause for a minute in case you wish to have some other questions or interactions. Okay, a CTUR, I guess I got your question. The question is why reference circle of the involute is a base circle. As I said, by definition, when we say it's involute, we generally mean it's involute of a circle. Involute of a circle means the locus of a point on a string as that string is unwound from a circle. So this is just the definition of involute, that you have to unwind the string from the circle. So that's why the reference is that of a circle. So I take that question as answered. KECP is asking the driver and driven diameter are not the same in the cross-belt pulley analogy. Why? Obviously, if the driver and the driven diameter is same, then the velocity ratio is unity. But you want the gear or the cross-belt pulley drive to work for different conditions of velocity ratio. So to get a different velocity ratio other than unity, you need the driver and the driven to have different diameters, which is what I showed in my drawing. The cross-belt pulley analogy demands, or I would say works for any velocity ratio between the input and the output, and that is what has been shown schematically in the diagram. So I take that as answered. Okay, since there are no other questions, I will turn back to the lecture material and will now quickly define a few parameters associated with the involute gear geometry. So the first of them is pressure angle. Pressure angle is the angle that is between the direction of the force transmission and the common tangent at the pitch point, okay, the tangent to the pitch circle. So here you see the two gears, the two involute gears are meshing. As we said that the force that is getting transmitted between the gear tooth pair will be along the common normal, at least if it is sliding frictionlessly. So the force that you can expect to be getting transmitted from the driver to the driven. So the driver is the gear which is shown on the right and the driven is the gear which is shown on the left. So the force that is getting transmitted between these two bodies would lie exactly on the common normal between the two gear tooth, which we now understand is also the tangent to the base circle, the internal tangent to the base circle. So these two are the base circles which are shown. This is the base circle for the driven gear on the left, and this is the base circle which is shown in the black dotted line with the base circle of the driving, which is also the pinion or the smaller gear. Now the common tangent between the base circles, but this tangent is an internal tangent, this is not an external tangent. So this common tangent happens to be the belt from where this involute is generated, that is using the cross belt pulley analogy. So therefore the common normal is between the involute is given by this line, which incidentally is the common internal tangent between the two base circles. So the force transmission occurs along this line, whereas if you now think in terms of friction discs and pitch circles, therein the force transmission which results in a torque is along this vertical direction. So the angle between these two is called the pressure angle. Okay. So pressure angle is the angle between the common tangent to the pitch circles and the common internal tangent to the base circles, right. So let me just draw this figure once for you to illustrate. So these are the base circles drawn in black. These are the two base circles. I am just blowing things up. So therefore this is the internal tangent to the base circle. So this line is the internal tangent to the base circles. This is also equal to the common normal of the involutes. Now, if I recall that the pitch circles will have this sort of a profile. So, let us say the pitch circle, which are like two discs, right, two friction discs which transmit equivalent motion due to the action of friction. So, here this is the force that is getting transmitted due to the two friction discs which is causing the torque. So, this is the direction of the force, it is along this red dotted line. So, this angle between the force transmission as occurring in a true gear pair between a gear tooth and the point of C and the common tangent between the two pitch circle is called phi, the pressure angle. So, phi is called the pressure angle. Okay. So, usually it is about 20 degree as per standards, but that is besides the point. So, here now if I do this geometry a little more carefully, I should be able to understand the following. So, here I am completing these lines. So, this line is tangent to the radius vector as we know. So, this is RP, which is the pitch circle, and this is RB, which is the base circle. So, if this is phi, this is also phi, and this is 90 minus phi, right. So, therefore, RB is RP cos phi. RB is RP cos phi. So, this is the relation between the base circle and the pitch circle. Okay. This is the relation between the base circle and the pitch circle. I have just zoomed in to this triangle. So, you can call this OAP. So, from triangle OAP you get the relation that the base circle and the pitch circles are related through this relation, which is a cosine relation involving the pressure angle. Okay, so RB is RP cos phi for both the driver as well as the driven. So, the pressure angle as we have defined is the angle between the common normal at the point of contact and the common tangent to the pitch circles. Again, the common normal at the point of contact between the two involutes is nothing but the internal tangent to the two base circles. So, the common normal at the point of contact is internal tangent to the base circle, which is what I have written here. So, the force that is transmitted between the gear pair is along the common normal. That is very important because as Ujjwal Rane said, it is a positive drive. So, there will be a force that is transmitted from the driver to the driven, and that force transmission, assuming that the body the contact is taken in a frictionless manner, because we are not accounting for any dissipation mechanisms within our gears. So, the force will be transmitted exactly along the normal direction. But you will recall that the torque that will get, what we are interested is not the force, we are actually interested in the torque. Now, if the force is getting transmitted in along this direction, which is slightly slanted from the vertical, one component will come to the horizontal direction. The horizontal component of this force, which is acting in a slanting manner, is actually not useful in creating the torque. The torque will come only because of the vertical component. So, the cos phi component of the force transmitted is actually responsible for the torque. So, the torque is pitch circle radius into F cos phi. So, in other words, even as we know, RP cos phi is the base circle radius. So, this is also equals to force times the base circle radius. But what happens to the other component, the horizontal component? So, the horizontal component, if this is the force which is acting in a slanted manner, slanted to the vertical by angle phi, then f sin phi denotes the horizontal component. So this horizontal component is useless as far as torque is concerned, but then it may cause shaft deflection, because finally the gear is mounted on some shaft and the shaft is mounted on bearings which is supposed to connect to the frame. So therefore this the gear, since it is attached to the shaft, which is like a you can assume that to be a beam of circular cross section, if there is this horizontal component that is passing through the gear center or the shaft center, so that is like a transverse load onto the shaft. So this transverse load onto the shaft will cause shaft deflection. What will happen if the shaft deflects? If the shaft deflects or sags by a huge amount, then the gear pair will no longer be in contact. So the gearing action will be lost. So therefore this is actually a menace. So if you have a large f sin phi which is directed towards the center of the shaft, then that will cause a shaft deflection. So this actually leads us to a very important criteria, that if phi is taken large, then sin phi component will be large, f sin phi will be large, and this will cause large shaft deflection. So we want to avoid that, so we will not take a large phi, we will rather like to live with a small phi as possible, as small phi as possible, but then we cannot take it to be 0, because if we have to have involute tooth profile, then we must have the two base circles which are lesser than the pitch circle radiuses. Now if there are two base circles which are lesser than the pitch circle radius, then obviously their internal tangent to the two base circle cannot be exactly coinciding with the tangent to the pitch circle, cannot be vertical as in my drawing shows. So therefore phi equals to 0 is not possible from practical considerations. At the same time phi should not be too large, because that will lead to large shaft deflection. So therefore we have to have a compromise for the pressure angle, and again as a part of standardizations, pressure angles which are usually there in operation is 14.5 degree, which actually is primitive. 14.5 degree is rarely used these days. 20 degree pressure angle gears are most commonly used. 25 degree is also available as per standards. As I said, mostly gear manufacturing and gear design relies on these standards. You should think about how to buy these gears off the shelf. If you are trying to buy the gears off the shelf, then these gears will be made as per these standardization procedures, and one of those standardization procedures demands that the pressure angle be 20 degree. Again, there are different standards as is applicable. SI standards are there, AGMA standards are there. AGMA is American Gear Manufacturing Association. So different standards will have variations in their recommendations, but these are the different pressure angles which are widely used in the industrial applications. So I will show you some of these standards in due course, but let us now continue. As we now understand that base circle of the gear is the base circle from which the fictitious string is getting unwound to generate the gear tooth. So the circle over which the unwinding action was taking place is called the base circle, or even in other words, from the cross bolt pulley analogy, if we base circle is exactly the radius of those two pulleys which were connected by the cross belt, and when the cross belt mechanism was moving, then each of on each of these pulleys you are getting the involute tooth profile. So remember, the cross belt pulley analogy essentially should convince you that you are replacing the cross belt drive with the gear, where the cross belt drive will have the pulley radiuses to be equal to the base circle radius. So that is the base circle for you, and in this figure which is taken from Shigley's book, base circle is shown in this diagram. So this is what is base circle, right, for the wheel, that is, and for the pinion base circle is shown here. Please note that the base circle formula as we have derived is given as RB equals to RP cos phi, whereas this is not a constant. Depending upon the value of phi and the pitch circle and everything else, as we will show, that it is possible to have base circle to be greater than the dedendum circle or lesser than the dedendum circle. All that we know that the base circle is lesser than the pitch circle radius, because the formula says RB equals to RP cos phi. Now phi is definitely not 0, which means cos phi is lesser than 1. Therefore, RB is less than RP, that is known. But and similarly, since addendum circle radius is more than the pitch circle radius, because addendum is a positive number, so therefore base circle is known to be smaller than the pitch circle or even smaller than the addendum circle. That is unambiguous. But what is ambiguous, at least at this stage, is that this formula does not prevent base circle radius to be greater than dedendum circle radius or lesser than dedendum circle radius. Both the possibilities are possible, and here we see in this diagram that for the smaller gear we have the base circle to be actually larger than the dedendum circle, whereas for the larger gear or the wheel as it is called, the base circle radius is smaller than the dedendum circle. So dedendum circle is bigger. So both the possibilities exist, and this will have major implications in our understanding of interference, as we will talk about. So the issue of interference comes in the following manner, that we understand that the involute tooth profile. So let us say this is the base circle. The involute tooth profile can extend only outside of the base circle. There is no way that the involute tooth profile can extend below the base circle, because by definition involute is the type of curve which is generated by unwinding a string from a base circle. So there is no way you can unwind a string and get a curve which is on the interior side of the base circle. That is not possible. So therefore the involute tooth profile has to exist only outside the base circle. But so there are two situations which can now occur. So I will show that in two different cases. So let us say this is the involute tooth profile, and let us say the dedendum circle is larger than the base circle. So the dedendum circle is larger than the base circle. So that means the actual gear tooth profile would have ended here. Oh, sorry. So I need to draw that once again. So this is the gear tooth profile, and the dedendum circle is here. Okay. So therefore what I see in the physical construction is only this part. The red part is not seen in the physical construction, but this is a happy situation. I am at least sure that this part is involute, no issues, because the involute can be there at any portion which is beyond the base circle. So I must make it clear that what is drawn in red is the base circle. So this is the base circle, whereas this is the dedendum circle. You will recall that dedendum is where the gear tooth profile ends. There is nothing below the dedendum. Now let us look at the second case where you have the dedendum circle to be lesser than the base circle. So as usual, this is the base circle and this is the gear tooth profile which can emanate only in the region beyond the base circle. So here we have the situation that the dedendum circle is smaller than the base circle. So again this is the RD or the dedendum circle, and this is RB or the base circle. So this is the case where base circle is more than the dedendum circle. So now you have a problem. The physical construction which must be drawn in black, because the base circle is again an imaginary circle which is not seen in the physical construction. In the physical construction you can make out for the dedendum. So now the question is, what happens in the part which is between the dedendum circle and the base circle. So here, as we understand, this portion cannot be an involute by definition, because no portion of the involute can go interior to the base circle. So here we make a very important observation which has major implications in our understanding of interference, that if the involute tooth profile can reside only in the portion which is beyond the base circle, not in the portion below the base circle. If at all it is there, it is not involute. So manufacturing processes will ensure that if dedendum circle is actually lesser than the base circle, this black portion is basically just the radial extension. So we just sort of extrapolate the profile, and that extrapolation is done radially, but definitely it is not going to be an involute. And as such, if at all there is contact in this black portion, then you are going to have a loss of the conjugate action, and the fundamental law of gearing is going to be violated, and there are other repercussions in interference, as we will see. So this is a comment that I made at this stage, that by the manner in which we have constructed the geometry, it is possible that the dedendum as well as the can be greater or lesser than the base circle. But when the base circle is greater than the dedendum, then all that we can do is that the tooth can be radially extended inwards. That is what is being done. So as I said, this is the this is one standard dimensions of a geared tooth, and this is as per SI standards taken from a book. So the pressure angle, as I said, is mostly 20 degree or 25 degree in case of coarse pitch is also used. Addendum is 1 module, dedendum is 1.25 module, working depth, hole depth, circular tooth thickness, everything is mentioned as in this formula. So these are standard formulas. It is just that we should use these formulas so as to be able to work out the geometry. Now please note, all that we know about the dedendum is that it is 1.25 module. This is the only specification, or similarly if it is fine pitch, then it will be 1.4 module. So in either case, both of these conditions are possible. That is the crucial to realize, that if you take one or the other, both can be possible. There is no way you can rule out one possibility. So this, as I said, we have major implications in our study of interference. But before going at interference, let us understand once again that how does the engagement of a geared tooth actually takes place. So here I have drawn only the circles. So by now we have three very important circles which we should try and understand. One is the base circle. So these are shown in blue color. So the base circles we understand are the driver and the driven pulleys, which we have understood from the cross belt pulley analogy. So now we understand that the involute will be generated as a string is being wound or unwound from one of these two pulleys. So this is the base circle corresponding to the gear pair. The gear pair can be replaced with a pair of friction discs which transmits equivalent motion. Those friction discs are called the pitch circles, and the pitch circles here are shown in green. And finally the addendum circles are shown in red. So the addendum circles are shown in red here. So pitch circle to addendum circle, the radial distance is 1 module, as we have seen. The pitch circle to the base circle, we have a cos phi relationship, as we have seen. So these are the three circles shown schematically. Please note that the pitch circles will have a tangency condition met at the pitch point, and exactly at the pitch point the tangent between the two base circles should pass, which is sort of made clear in this schematic diagram. Now we must understand how does the engagement point move. So the engagement point is moving from this point, which is known as start of engagement, to the end of engagement, which is shown in box here. So the end of engagement is denoted here. So the point where the engagement starts is the point of intersection between the addendum circle and the tangent to the two base circles. So start of engagement is the intersection of the common normal, which is shown in black color, of common internal tangent to the two base circles, which becomes the common normal of the two involute tooth profiles. Wherever that intersects with the addendum of the driven, that is where the engagement starts. Similarly, the engagement finishes. The end of engagement is where this common normal intersects with the addendum of the driver. So this is like the last point where the driver pulley is having any grip, or the driver gear, I should say, not the pulley. The driver gear is having the last engagement with the driven pulley at the point of its addendum. And we know the point of contact anyway has to lie on this black line, which is the common internal tangent between the two gears. Between the two base circles, I am sorry. So the, as is inferred, that the point of contact definitely has to lie on this common normal. The end of engagement happens when the addendum last intersects this common normal. The start of engagement happens when the addendum from the driven gear side gets into this point. So when this, so the point of contact will move from this blue dot to this blue box, and it will move on this black line. This is exactly what you have seen even in the animation. If you realize, the start of engagement is happening right at this point. If you see, this is the point where the addendum of the driven gear. So this is the driven gear is on the right. The addendum of the driven gear is intersecting the common normal between the two involutes or the internal tangent to the base circles exactly at the point where I have kept my mouse, right. So this is the point where the engagement is starting between the gears. Similarly, the engagement is finishing at this point where the addendum circle of the driver gear is intersecting within the with the internal tangent. So again, this is the geometry of engagement of the gears. This idea will be extremely important both in the derivation of interference as well as in the contact ratio derivation, which hopefully we should be able to do in the next class. But you must understand the geometry of the gears very nicely such that you are able to derive those results. So the start and end of engagement is given here. So let's quickly go through the advantages of the involute tooth profile before we finish the class today. As we said, the fundamental law of gearing is satisfied, which essentially means that the velocity ratio is constant for all times during the course of meshing between these gears which are made of involute tooth profile. Another very important characteristics is this, that the pressure angle is constant, because what is pressure angle? The pressure angle is the angle, if you look back at the definition from this geometry, the pressure angle is the angle between the common tangent to the base circles and the common tangent to the pitch circles. Now the base circle does not change in the involute, which means the common tangent does not change in the involute. Therefore, similarly the pitch circles does not change, which means the common tangent to the pitch circle does not change, which means the angle between the common tangent to the base circle and the common tangent to the pitch circles also should not change, and this angle is called pressure angle. Now what is the problem if the pressure angle changes? As we said, if the one component of the pressure angle is responsible for the shaft deflection. If the pressure angle changes during time, then the shaft deflection will change with time. So we will get dynamic shaft deflection, which is very bad in terms of the noise and vibration characteristics of this transmission. So dynamic shaft deflection should be avoided. It can lead to fatigue failure of the shaft also. So the dynamic shaft deflection does not arise in case of involute gear action, because involute gears by its very nature the pressure angle is kept constant, which means that the shaft is always subjected to a constant force, and therefore the question of dynamic shaft deflection does not arise. This another very important advantage from the perspective of manufacturing is that during manufacturing it will definitely happen that the shaft distance will change due to the assembly related inaccuracies. What happens is that the worker will try to force fit one gear and ensure that meshing action just takes place. So in so doing, in this manual fitting exercise, the worker naturally will be sort of subjecting these two shafts to a little more additional forces and will try to force fit these two gears. And in so doing, the shaft deflection, the center to center distance between the two shafts, the input and the output, will change maybe by a little amount. It so turns out that these assembly related inaccuracies can be accommodated very nicely with the help of involute gearing, and this will be accommodated by simply a small change of pressure angle. Our gear ratios will remain unaffected. The gear ratio will not change due to such assembly related inaccuracies. What will change is just the pressure angle, and we will show that through a calculation probably in the next class. So at this stage I will just ask you to take this on good faith that if there is a small change in distance between the gears due to assembly related inaccuracies, that can be accommodated by our involute gearing, and the only repercussion of such assembly related inaccuracies will be change in pressure angle. The gear ratio will remain unaffected and the gear ratio will be held constant for all times. So nothing of those sacrifices will be made. The only compromise will be in the pressure angle calculation, which is what we will show probably in the next class when we meet. From the perspective of manufacturing, it may seem that making a gear out of the involute tooths will be more specialized and more demanding in terms of manufacturing, but actually this is not true. As again I will probably be able to derive that it so happens that the gears are one way of manufacturing gears is through a rack cutter. So we know what's a rack and pinion arrangement. So it turns out that the conjugate profile on the rack which sort of meshes with the involute tooth on a gear is that which is straight tooth. So as this rack is meshing with a circular gear, it will cut out an involute gear naturally. This is very nicely shown in one animation of again kinematics with microstation channel in YouTube. Please look at it, but at this point I will simply suffice to say that the fact that the rack cutter corresponding to an involute tooth is actually straight faced. So therefore making that rack cutter is very easy, and when you have that rack cutter and meshing on a circular gear blank, naturally it will generate out this involute tooth, which makes the involute tooth a real good advantageous in terms of manufacturing issues also. So I think I will end here. We will start from here in the next class where I will demonstrate this third bullet, that how assembly related inaccuracies can be accommodated through involute gearing through a problem, which I will demonstrate probably in the next class, after which we will quickly give you the results of contact ratio and interference, and then we should have some time left to do some gear train analysis also. Okay, so with that I will close today's lecture, but in case you have any questions around the lecture material presented thus far, I will be happy to respond. I see some questions already posted, let me look at them. So the next question is, if the pitch point is not constant but the ratio of instantaneous center remains constant, then is it possible to construct gear profile? That is actually not possible. The ratio cannot remain constant if the pitch point does not remain constant, because if you recollect, the geometry is, so I12 is fixed, I12 is fixed, I13 is also fixed. If you allow P to be varying, there is no way you can keep this ratio I12P by I13P to be constant. So by fundamental law of gearing, you want this to be constant, right? This ratio to be constant, but I12 and I13 are already constant. They cannot, they are just fixed to the ground. So therefore they are constant. So therefore the ratio will be constant if and only if P is constant. So that's the requirement for fundamental law of gearing. But in cycloidal gears, for example, what happens is this: what we have seen in involute gears is that the common normal also is fixed during the course of engagement. That is not required as part of fundamental law of gearing. You could have the common normal changing, but the point is, even if the common normal changes, fundamental law of gearing says that it should pass through the same pitch point, or in other words, the intersection of the common normal and the line joining the gear centers should be fixed. So it is not necessary that the common normal be fixed. So common normal can vary. However, it so happens that in involute, for involutes, common normal also is fixed. But this is an overkill. You need not have a fixity of the common normal. In cycloids, the common normal doesn't remain fixed, yet it is able to achieve fundamental law of gearing. But then if the common normal changes its direction, as I said, then there are issues associated with dynamic shaft deflection. So that is one of the disadvantages of cycloidal gears. So I hope that answers your question. We will move on to the next one. BEC is asking, why is the base circle always taken below dedendum circle? That is precisely the point. Base circle is not always lesser than the dedendum circle. As I showed you in the slides here itself, base circle and dedendum circle, there is no rule which says that base circle has to be always lesser than dedendum circle or always more than the dedendum circle. In this picture, what is clearly shown on the gear, base circle is lesser than the dedendum circle. On the pinion, base circle is more than the dedendum circle. So either of these two conditions can be met. This is a figure taken from Shigley. So some books are actually showing this carefully, that base circle can either be larger or smaller than the dedendum circle. There is no rule which prohibits either of these alternatives. So base circle, to answer your question, BEC, base circle is not always taken below dedendum circle. If some book you have seen is showing it, that is erroneous. I mean, it is erroneous in the sense that it is not general. You may have under some condition base circle to be below dedendum circle, but some other conditions it does not rule out the possibility that base circle is above the dedendum circle also. Both are possible, as is shown in the figure in my slides. AECP is asking, why only involute gears satisfy fundamental law of gearing, and what about cycloidal gears? As I said, involute gears does satisfy fundamental law of gearing, but I think I made the remark that this is not the only profile which satisfies fundamental law of gearing. There can be other profiles also which satisfies fundamental law of gearing. For example, even a straight tooth profile can be made to satisfy a fundamental law of gearing, but the conjugate to a straight tooth will not be a straight tooth. That is very important, right? So it is, I never said that involute gears are the only tooth profile which satisfies fundamental law of gearing. As you said, cycloidal gear tooths also satisfy fundamental law of gearing, but there are other disadvantages associated with cycloidal gearing. One of it is dynamic shaft deflection. Involute gears wins because of all the four advantages put together: ease of manufacturability, ease of standardization, ease of assembly, no chance of dynamic shaft deflection or fatigue index failure. So these questions are, this is what sort of makes involute gears preferable. Please understand, theoretically it is possible to make any tooth profile satisfy fundamental law of gearing, including the straight tooth profile, but such a theoretical tooth profile would actually make the life very difficult in terms of manufacturing and assembly. So therefore, involute tooth profile definitely has the advantage of satisfying fundamental law of gearing. It also has other added advantages, all put together, as I showed in that previous slide, makes involute gear tooth profiles as an ideal candidate for wide application in the industry. Involute gear tooth profiles are not the only profile which satisfy fundamental law of gearing. Other gear things also satisfy. Okay, that answers the question. CTOR is also asking what is the difference between coarse pitch and fine pitch. I think that is remarked there itself in the slide. By coarse pitch we mean module which is more than 1.25 mm, and by fine pitch we mean module which is less than 1.25 millimeters. So as I said in the first class, all the gear dimensions are referenced with respect to module or circular pitch, and in SI standards it so happens everything is referenced with respect to module. So again, as per the standardization procedure, they have made these dimension standards in two groups, one group in which module is greater than 1.25 millimeter and the other group in which module is less than 1.25 millimeter. Module less than 1.25 millimeter, you will recall the pitch is nothing but diameter divided by number of tooth. So fine pitch essentially means larger number of tooth. For the same diameter of the gear you have larger number of tooth. So that is what we call a fine pitch gear. The exact qualification of it is this. If your question is why have they selected 1.25 millimeter and not let us say 2 millimeter or 1 millimeter, that is a part of standardization. They have just sat down and decided 1.25 millimeter is the critical point, and below which they will call it as fine pitch and beyond which they will call it as coarse pitch. That is just a part of standardization. We have no role to play here. Okay, I hope that question is answered. Specific application of cycloidal profile. Cycloidal profile tooths are used, for example, in clocks. In clocks, these days you don't have anything but electronic clocks, but earlier when clocks used to have a lots of gear train arrangement, and some of those clocks would have cycloidal gear tooth profile, but as I said, most machine gear tooth machines gears will be involute rather than cycloid. So cycloid is pretty outdated by now. Okay, and sometimes even in toys you have these cycloidal gear tooths. I think toys also have cycloidal gear tooth. As usual, please feel free to post questions in the course pack either by yourself or with the help of your teacher at the host institute. So I should be able to resolve your queries. Also look at the lecture material which is posted on the course pack. If you want, please go ahead and take a printout of it and study the material. The reference books also I have given from which this material has been drawn. Definitely there are lots of helpful resources available in the web which animates these different mechanisms and sort of makes your visualization easier for you. So please go ahead and use them. I don't think there are any other questions pending in my tab or anyone hand raised. So if there are no other questions at this stage, let us call it a day for this class at least. We'll meet in the next session again. So hopefully that time we should be able to talk a bit about contact ratio, interference and gear train. So that's the remaining agenda for the next session. So see you then. Have a nice day ahead. Thank you.